तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last class we discussed about the representation of numbers and some of the errors that can come because of this finite representation of errors. We continue on that today and see some concrete examples of these errors which comes. And we said that the errors are two different types. One is mainly two different types. One is the round off errors and other is the truncation errors. Now these errors we can quantify and we can write an error as the value obtained minus the true value divided by the true value, and we call that as a true error, and multiplied by 100 would be the percentage error. But we saw that in real applications we would actually not know what the real value is, and thus we need another definition of the error, and that is what is shown here. So we set an approximate error. So the approximate error would be the way it is defined is epsilon a, to show that it is actually an approximate error. That should be the percentage error would be approximate error divided by approximation into 100. So what would be the approximate error? So that would be, for example, in a series, if you make two different approximations, you could take the differences between these two and then take the divided by the present approximation, and that would give us an approximate error. So you would see this in an example here. Just to remind you that A is used to show what that this is an approximate error. Okay, one place where we actually use this approximate error is in iterative procedures. So that is, as I said, the approximate error then would be between the difference between the present and the previous approximations, and then you could divide that by the present approximation to get the approximate error. So one could ask the question whether I should take the previous approximation minus the present approximation, or the present approximation minus previous approximation, or does the sign matter? But we are not generally concerned with the sign, we are only concerned with the magnitude, so we could write it either way, okay, and define that as the approximate error. So when you are doing a series expansion, one would be interested in making this approximate error less than the machine tolerance. Okay, and we saw what this machine tolerance would be, right? And we said that if you want to have a precision of n digits, and then the tolerance which we can calculate is 0.5 into 10 to the power of 2 minus n percentage. So that would be the, so this means that we have n significant figures. So we can compute an approximate error in a series expansion, and then we could demand that the series, you keep the terms all the way up to a term such that the sum is less than, the error is, approximate error is less than the tolerance, where the tolerance we could fix to be 0.5 into 10 to the power of 2 minus n, where n is precision of the machine or the significant digits which we are interested in. Due to some reason We may not be interested in going all the way up to the machine tolerance, because there is some other part of the computation which does not have that precision. For example, when we take experimental data and then we want to do some analysis with this data, most of the time the measurement itself is not precise beyond certain number of digits. So, there is no point in keeping very high precision, which will only introduce additional errors. Okay, so, we could just cut them off and we will keep a certain number of figures. So, we will go look at an example of this iterative method just to drive home the point that what we mean by this approximate error. And so, let us look at this case of where we try to compute e to the power of 0.5. So, we will use a series expansion to actually compute e to the power of 0.05. We know the true value in this particular case, and that happens to be 1.648721271. I happen to know this value here. So, what would be the series expansion we would use? So, we would expand e to the power of 0.5 e to the power of x in general as 1 plus x squared by 2, etc. And then let us say we to take an example, we want this to be kept up to 3 significant digits. Let us say we want to do that. So, then what do we find? So, we would want to have a tolerance of 0.5 into 10 to the power of 2 minus 3, I said 2 minus n. So, here is n is 3, so 2 minus 3, that is about 0.5%. So, let us look at that series. Okay, the series is e to the power of x, as I said, 1 plus x squared by 2 factorial plus x cubed by 3 factorial up to x to the power of n by n factorial. So, the question is up to what n I should go, that would depend on. So, that will depend on what accuracy I wanted. So, I am going to do that. I am going to compute two different errors here, the true error and the approximate error, and then we could demand that it should go below the tolerance which we wanted. Okay. So, let us start with that calculation. The first term is simply 1, right. So, and the second term would be 1 plus 0.5 for e to the power of 5, that is 1.5. So, now what will be the errors which we have? Okay, so, the true error would be 1.648721271. That is a true value minus the approximate value divided by the true value, that is 9.02% error. So, then we could take the approximate error. The approximate error is 1.5 was the present approximation. The previous approximation was 1, and we divide by the present approximation. So, that gave us 33.3%. So, then you could go to the next term, right. You could keep the x squared by 2 factorial term, and then we could increase we could decrease this error. So, now the point is we will continue this series, that is how we compute this. Okay. So, we compute the next term, we would keep x squared by 2, right. So, that will give us 0.25 divided by 2, so 0.125, okay, and then we add that to this, right, and then we again subtract 1.5 from this, right. So, we get, when you add 0.125, we get 1.625, we will subtract 1.5 and divide by 1.625, that will definitely give us much smaller error than this. So, we could compute it in this way and then go up to the series where it goes below the tolerance which we have specified. We will see later that this it is not guaranteed that when you go higher and higher in the series that you will going to get a better precision or better value. Okay. There will be other reasons why there is a limiting value to a machine. Okay. We will see that in later. Okay, so we summarized this computation which we did just now, that we said 1.1 first was 1, so we had got a true error of 39.3%. If you just take 1, okay, that is 1.625. Sorry, 1.648721271 was the correct answer. So we can compute the first approximation as just as 1, and then there is a true error which is very large, and we don't have an approximate error because it is the first approximation. The second approximation was 1.5, and then we have a true error of 9%, and we have an approximate error of 33.3%. So in this case we can compute the approximate error because we have a second approximation. We have a first approximation and a second approximation, so we could do that. And the third approximation would be adding the x squared by 2 term, and that will give a 1.625, and then we would compute the approximate error by now taking the difference between these two divided by this number. Okay, so that will give us this. And when we go to the fourth term, then we will again take the difference between these two numbers and divide it by this number. Okay, so that will give us the next error, estimate of the next percentage, approximate error, etc. That is how we compute. Right? Okay, so then we would say that okay, I was demanding 0.05% as my error. Now by the time I reach the sixth term, I have gone below 0.05%, so I can stop my computation here. Okay, that is an example of how we can use this error estimate to compute something. So let us just summarize this once again. There are two types of errors encountered in the numerical calculations. We said one is a round off error due to finite representation of numbers. So for example 1/6 cannot be represented exactly, right? So we have to have a finite representation to this. Now there is an error due to this which can come because when I take 1/6 and if I approximate 1/6 by a finite number of digits and then multiply it again by 6, I would expect to get 1, but I would get something different from 1. So that's the answer. Okay, so we will see how we can write a program to actually demonstrate these errors. Okay. So let's just look at that. Okay, that will also help us to get familiar with small programming. So we did look at some of the elements of programming before, so but let's just put it into practice and then look at some small programs. For example, here we will see how I can approximate 1/6 to a certain number of digits, okay, and then try to compute the errors from that. As I said, sometimes in the experimental data analysis we need to restrict the calculations to a certain number of digits. We do not want to go beyond that. So how do we do actually this chopping and rounding which we said before? That is 1/6 we can either chop off or round off up to some number of digits. So how do we do that? So we just look at this, an example. So here is a simple code to limit the number of decimal points in some variable in the calculation. So I will write a small code like this. So I have only a main program here, and I have declared an integer and two floating point numbers, integer as I and floating point numbers as y and x. And I define my x up to 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal points in base 10. So now let us say I want to limit this to 2 decimal points. So how do I do that? Okay, so I would do it in the following way. Okay, so I will take this number, right, and I will multiply. I take this number here x, okay, and I will multiply it by 100. So I will get 53.4085734, right? Okay, and then I will multiply it by 100. I will get the 53.40875, and then I take the integer. Okay, floor is here as a function I call floor, which basically what it does is to convert this number to its nearest integer and gives me an integer as an output. So I is an integer. So if I take x and multiply it by 100 and take floor, I will get 53. And then I will divide that by again by 100, 100.0, and I will make another floating point number. So that will give me 0.53. So I basically, in this process, I have chopped off everything beyond 2 digits. So that's what you would see here. If I run this program, you will see that that's what I will get. Okay, so I started with 53 points something, right? Okay, and then I made an integer of that's 53, and I made that again into a floating point, so I got 0.53. So ignore the zeros because that doesn't mean anything here, because I chopped off all numbers below 3 here, below the second decimal place. So this way I can approximate numbers to certain decimal places. So now we can use this to actually do this 1 by 6. Okay, so I'll put my x as 1 by 6. Remember, when you define a floating point and you're writing a fraction, always have to write that as a fraction of 2 floating points, or at least 1 floating point. If I write 1 by 6, this will go to 0, but x is an integer, x is a floating point. It will look for an integer if I just write 1 by 6. Okay, so now I'm going to approximate that to 2 decimal places, and let's look at what we get. Okay, so we got 0.16, right? So the actual number should be 1.66666. You can see already here it has been rounded off. Okay, so 666 it continues and it has been rounded off to 7, but I even further reduced that and I made just 2 decimal places and I chopped it off. Okay, I just simply chopped this number off after the second decimal places. So there's a chopping. Right? So now we can also do rounding. So what we have to do there is to make and add a 0.5 to this. Okay, and then run that. Okay, so then we would get it's rounded. Okay, instead of 0.16 which we got here, now we get 0.17. Okay, because the next decimal place is more than 0.5, so that has been approximated. So this decimal place has been approximated as 7. So that is example of chopping and rounding. So now if I just take this 1 by 6, let's say I had only a 2 decimal place computer. Okay? So I would have 1 by 6 rounded off as 0.17. Now what will be the consequence of that? So consequence, for example, here I had said that if I take 1 by 6 and multiply it by 6, okay, again rounded off to 2 digits. Right? So what do I get? Okay, that's what we should look at. So we should try to print here one more term, so that is 1 by 6, which is our y. Okay, 1 by 6 approximated to 2 decimal place was our y. Okay, now we will multiply that by 6 and then see what we get. We have to multiply this by 6. So it's y is 1 by 6 and we multiply this by 6, and that's what we want to look at. Okay, so we definitely don't get 1, we get 1.02. So that's a kind of errors which we are talking about coming from round off errors, because we decided to actually reduce the or to keep the precision or the number of significant digits, which is also precision, only up to 2 decimal places. And as a consequence of that, if you take 1 by 6 and multiply it by 6, 6 being an integer, okay, 1 by 6 multiplied by 6, we find that we don't get 1 and we get 1.02. So in this case, and then we can also see how it will be if I just round it off instead of chopping it off. Okay, so that will be interesting to see that there is a difference between these two values also. Okay, so we got 0.96 instead of 1.6. Okay, so that's because I have restricted this into 2 decimal places. If you keep more decimal places, you get slightly better answer. Here, for example, it is kept to 5 digit, and then you got 0.9996. Okay, it's much better answer because it has got 5 digits here. Okay, so that is one kind of error. Okay, so then we have also rounding of errors which appear due to arithmetic operations with finite digit floating point numbers. Not only because of the representation of the number itself being rounded off, as we said 1/6 being rounded off to 0.17, but also because the arithmetic operations involve also incorporate round off errors. So this is a major source of error again. So here are some examples for it. We can look at one of the examples here. That is, if you try to compute e to the power of minus 5.5. So we can use a series as we saw before, right? We could say that I will compute e to the power of minus x with a series, e to the power is 1 minus x plus x squared by 2 factorial plus x cubed by 3 factorial, etc. Now I will define a function which gives me this just to approximate my errors, right? So I can just to quantify my errors, I will define the function as up to n terms as this function. Okay. And you could plot this function value at x over minus 5.5 for different values of n computed in 5 digit floating point arithmetic. Okay. And then you would find that this value, as you keep on increasing n, would saturate beyond some point. Okay. So that's the thing. We will try to again look at this saturation with an example. Okay. So let's look at that for example with that kind of a series. So we want to compute x to the power of minus 5.5. That's what we wanted to compute. Okay. So let's compute that. So we will keep this term as minus 5.5. So and then we would just, so what I'm doing here, so I have a small program here. Okay, so again I defined some integers and I have some floating points y and x. So I started with x equal to 1 because my first term in the series is 1. Okay, so that will be the first term in my series. So I kept it as starting to 1. Okay, and my power here, okay, which I call y in this program. Okay, I'll just change this to, so let's start with this as x and this as y. So we have y, the function f here, which is called y, okay, is 1 to start with, and I have the power which is minus 5.5. And then I run it through a series. Okay, I'm going up to 10 places. Okay, that means 10 terms. Okay, I'll go up to n equal to 10 in the series. So that's basically what I'm going to do. Okay, I'm going to going from 1 to 10. And then I know that the denominator of the series goes as 2 factorial, 3 factorial, etc. up to n factorial. So to compute that, I have term j equal to 1 here, and j keeps going from j star I. So when I equal to 2, it is 2. When I equal to 3, it's 1 into 2 into 3, etc. I hope this is clear. So that we have j equal to 1 to start with. So when I is 1, j is simply 1, while when I is 2, that's the second term comes in. Okay. So the second term here would mean this term, index n equal to 2. Okay. When n equal to 2 comes in, so then it will be a 2 factorial, which is 2. So that's what the j would take. So j is become 2, and then when n becomes 3, then we have 3 factorial, which is 1 into 2 into 3. So the j was already 2, and then that gets multiplied by I equal to 3, so it goes from 3 factorial, etc. Okay, then I compute the nth term here. This is actually the nth term which I am computing, which is basically just this term. That is the nth term. That is minus 1. So POW is a built-in C function which will compute the power of something, right. So, I compute the power of minus 1 to the power I here, okay. That is minus 1 to the power I is computed using this function POW, which is a built-in math library function. And then I multiply that by y to the power of n, that is what I do here, sorry, x to the power n it should be, okay. So, that is exactly this term. So, I have minus 1 to the power n and I multiply that by x to the power n, and then I divide it by the j, which is my n factorial, okay. So, now again I want to keep this into 5 digits. So, I will multiply what we saw before. The way to keep it to 5 digits would be to multiply it by 1, 2, 3, 4, 5, so by 100,000, and then I take that function and divide it by 100,000. So, I take this z and divide it by 100,000, then I get up to accuracy up to 5 digits, okay. So, that should be y. So, now I am going to print this off. So, I am going to print the function here, the value of the function. How does it change as the series goes by? So, first starting from 1, okay, starting from I equal to 1, that means I start from here, okay. That is what we are going to look at, okay. So, let us look at that. Let me just make sure that we are doing is correct. So, we took 5.5 as x and we are multiplying x to the power of I and dividing it by j, which is the n factorial, and we keep 1, 2, 3, 4, 5 terms, and 1, 2, 3, 4, 5 terms here, okay. And then we are adding that to the series, and then we were trying to get into the, okay. So, we are trying to go up to 4 n equal to 4, okay. Let's go up to n equal to 4 and then see these terms one by one, and let's see whether it converge or not. So, we will be printing out each term by term, these values of x to the power n by n factorial minus 1 to the power of n. That is what we want to look at. So, let us do that, and so we will compile this program, and we will compile this program first and then we will run it. Okay, so, the first term which we saw was of course 1, because 1 into 10 power of minus 1 minus x plus x squared by 2. So, the first term is 1, okay, that I have not printed that out, and the second term, that is n equal to 1 term, this is n equal to 0 term, n equal to 1 term would be simply minus 5.5, that is what we see here. So, 1 minus that, or 1 plus this term would be minus 4.5, and this next term is 15.125, 5 places, okay, 5 digits is what I am keeping, okay. The whole computation is just done up to 5 digits, okay. So, I will keep 5 digits. So, it is 10.625, and the next term is again negative, okay, and the fourth term is positive, etc. Okay. So, our value which we are getting is going as minus 4.5, then it goes to 10, and then it goes to minus 17, then it goes to 21, etc. So, we say we are not reaching anywhere on this example. So, now the reason for this is, if you look at again summarized here. So, I kept it 5 decimal places, and I say first is 1, and this is the normalized floating point representation to base 10. So, first is 1, and the next term is minus 5.5 or 0.55 10 to the power of 1, and the next term is, we saw, was 15, that is 1.15125 10 to the power of 2, and the next term is minus 0.2733, that is 27.73 10 to the power of 2, etc. That is what we saw here. But the point is, sum is not going to converge, okay. So, now the reason for this is the following, is that we are actually trying to add and subtract numbers of the same magnitude, okay. So, now the final answer is actually, we saw, is very small, right. The final answer is something like 0.004087, right, that is the final answer, correct. But look at the numbers which you are trying to add and subtract, okay. So, that is of this order, okay. Okay. So, we are trying to do 5.5, 15, 27, 38, etc. Which are all much larger than the final answer which you want to get. So, basically we are trying to look for something which is much smaller than the numbers which are involved in addition and subtraction. Okay. So, we are actually losing significant figures. So, we are not going to get a very good answer by doing this kind of a series expansion in this particular case. It is a very typical example of a bad series approximation. So, one way to get rid of this is to this catastrophic cancellation, as it is called, of digits, okay, of precision or significant digits, is use a different type of series. So, instead of using e to the power of x, you could have 1 by e to the power of x. Okay. So, now what is the advantage? The advantage is that then we are just simply summing these terms, right. So, we do e to the power of x, instead of e to the power of minus x, we do 1 by e to the power of x. And then we are not doing plus minus here, now everything is plus, okay, and then we take 1 by that term, okay. That gives us much faster and much more reliable answer as 0.0040865. We can actually try and do this here, okay, and so instead of computing e to the power of minus that, we would just simply compute the plus term, okay. So, that is, we would just do e to the power of x, and our final answer then will turn out to be 1 by that answer, okay. So, instead of plotting 1 by, instead of printing out y, we should have to have 1 by y then. So, that's doing this. Now, I am going to do e to the power of x instead of e to the power of minus x. I am going to use a series for e to the power of x, that will be this, right. So, that's the series we are going to do here. We are going to do the power of x to the power of 5, where x is positive, and all term will be positive, because now I am taking power of 1 to the power I, which is 1. Okay. So, I just take the power series and then again approximate to 5 decimal places, and then I compute the value 1 by y. Okay. That is what which you want. Okay. Now, let us see what we get with this example. So, if you do the same thing here again, okay, so I am getting a value which is much closer. Okay, sorry, I am supposed to plot 1 by y. So, okay, so I am keeping the same terms here. Okay, I am just keeping the same terms here and then computing it. Okay. Okay, so I am keeping the same terms, that is x value 5.5. Now, it is plus. Okay, and then x squared by 2, x cubed by 3 factorial, that is 6, and x to the power of 4 by 4 factorial, etc. Okay. And now, I summed up these terms, and I am taking the 1 by that. Okay, that is the inverse of that. Okay, so I can see that this term is kind of converging into the value which I want. Okay, unlike the previous case where it was not converging at all. Okay, so here we are getting a much better convergence, and if you go into a series which is for some more terms here, okay, we would find that we have come very close to the value which we want. Okay, so we are going very close to the value which we want, okay, which we were not getting by doing e to the power of minus x with 5 decimal places. Okay, so that's a clear demonstration of cancellation errors, okay, or the catastrophic cancellation of errors. So, we can compute I repeat e to the power of minus x 2 different ways. Okay, we could compute them computed using a power series of 1 minus x plus x squared by 2 minus x cubed by 3, or we could compute it using 1 by e to the power of x, which is 1 by x plus x squared by 2 factorial plus x cubed by 3 factorial, etc. And what we find is that these two gives us very different results, and this is because of the loss of significant digits due to the fact that we are trying to get a number which is much smaller than the whole numbers involved in the arithmetic operation itself. Okay, so now that's one thing which we can see. Okay, so to summarize, we said two types of errors. So we have round off errors, and we have errors which is appearing due to arithmetic operations. That's what we just now saw. And then we have other types of errors which are truncation errors, which we said. So that is due to the use of approximation instead of a finite mathematical operation. Approximation instead of a finite mathematical operation. What I mean by this, for example, if you want to do sine of x, okay, instead of using sine of x as a finite mathematical operation, we could use a series for sine of x, and that could give us truncation errors. Okay, so that is, for example, we have sine pi by 3 is this value for n. If I just use a series and stop it at n equal to 0, that is number of terms in the series is n equal to 1, n equal to 2, n equal to 3, etc. Okay, and the correct value would be 0.86575. So now if I use only one term in the series, I am getting a value which is completely off, or if I use two terms in the series, I get a slightly better, and if I use 3 terms in the series, I get a little more better, etc. But anyway, what I wanted to show you here is that if you use a series for this particular function, okay, you will introduce some errors. So that is another type of error which you would have, called the truncation error. Okay, so that's the summary of errors which we have. Okay, so now this point is this: there are two errors, that is the truncation errors and round off errors can often compete with each other. Okay. As we saw that in the sine series, I can use one term in the series, or I can use 2 terms in the series, or I can use 3 terms in the series, and etc. up to n terms. And as I increase the number of terms in the series, I get better and better answers, we saw. But this is not always true. The reason being the previous one, in which we saw that as we increase the number of mathematical operations, okay, then you have round off errors introduced. Okay. So we are kind of competing between round off errors and truncation errors. Okay. So the increasing number of terms in a series will reduce the truncation errors, but this will increase the number of computations, right? So number of computation, number of operations, arithmetic operations, and that would introduce round off errors. Okay. So there is actually a competition. Okay, that's what I was trying to show here. Okay, so if you long step size, for example, or use less number of terms in the series, then you have larger truncation errors. Okay, but then if you then we have round off errors going down. So the total error which is dominated in the beginning, okay, in terms of step size, okay, which is inverse of the number of terms in the series. Okay. So if in terms of step size, if I have large error due to round off errors in the beginning, okay, while less truncation errors, but because I use large number of steps to get into one particular point. For example, if I want to actually compute some series up to for an interval of pi by 3. For example, sine pi by 3, I could use small values of sine. Okay, right? I could compute the small values of sine and go step by step, and then go into sine pi by 3. So that will means that the truncation errors are very low when I use small step size. Okay, while the round off errors are larger, but as I increase the step size, okay, I will have less round off errors, because to get to that point I have to take less number of mathematical operations. So round off errors comes down, but then the truncation error goes down. So there is a point at which this kind of balances, which is called the point of diminishing returns. Okay, that's a point. So it's not always true that if you use a large number of terms in the series, you get a better answer. That's what the point I want to emphasize here. So then now we could see that we have we are introducing errors when we do a mathematical operation. So that's one particular operation. Now the question is, can we say something about how does this error propagate down a program? This means we have a series of computations, okay, in a program. So now if I make an error and a round off error and or a truncation error at one step, how does it propagate? Okay, that's something which we should be looking at. Okay, so that's this part of the. This is what this part we will look at. So we look at error propagation in functions of single variables. To start with, we just try to quantify this, okay, and then we would like to look at in multiple variables, and then we would like to see some examples of this using programs. So let's first define this correctly. So we have a function f of x which is dependent on a variable x. Okay. Now let's say we introduce an error, okay, in x itself, that is representation. Because of representation, finite number of digits, there is an error in x. So how does that reflect on the function? The error, how does that reflect on the function? Or what I mean by this is, how much of this error in x will propagate to the evaluation of the function f of x. Okay. So that's what is called, that will be called propagation of error. Okay. So we assume that x tilde here, okay, is an approximation of x. Okay. Let's say x was 1 by 6, okay, and then we approximate it into 2 decimal places. Okay. That's one possibility. So that's one example. Okay. So or 3 decimal places we approximated x. Okay. So now we would find out the effect of this discrepancy between x and x tilde on the value of the function, okay, on the value of f of x. That's what we want to look at. Okay, or on our our aim here would be to approximate or to find out what is f of x minus f of x tilde is. I said estimate because we really don't know what f of x would be, because we may not know what x actual value of x is, right? So we are kind of approximate what the value of it is, or in other words, how much what delta x here, that is x minus x tilde, okay, right, and delta f. What is the relation between delta f here, which is the error in the function f of x, and the delta x, which would be x minus x tilde, which is the error in the function, error in the variable x. So what is the relation between these two? So that's something which we should try to see. Again, we are not interested in the sign, only interested in the mod. Well, okay, so that as I said, the problem here is that we don't know the actual value of f of x, right? Okay, so what we know is only f of x tilde. That's what we can compute is only f of x tilde. So let's assume that x tilde is close to x. Okay, we'll assume that. Okay. And then we will also assume that f of x tilde is a continuous and differentiable function. So we'll make two assumptions here, that x tilde is close to x and f of x tilde is a continuous and differentiable function. Okay. And then we can employ a Taylor series to compute f of x near f of x tilde. Okay. So that's a series which I have given here. Okay. That's a Taylor series of f of x. X is the real value, right? So f of x. So we expand this f of x in around f of x tilde. Okay. So f of x tilde is an approximation to x. We expand this. To expand this in this series called the Taylor series, we need to find the derivative of the function f, and hence this approximation that it is differentiable at all points. Okay. What I mean by this is that f is a smooth function. Okay, it doesn't have sharp kinks. So we'd expand this series. Okay, so first term is f of x tilde, and then f prime, that is f prime here means the derivative of f with respect to x at x equal to x tilde. Okay. Remember, f prime of x is derivative of the function which we know with respect to x at x equal to x tilde into delta x, x minus x tilde. And the next term is f double prime, which means the second derivative of f, that is del squared f by del x squared at x equal to x tilde divided by 2 factorial into delta x whole square. And the third term is the third derivative. Here the notation is f3 is the third derivative, that is del cube f divided by del x cube at x equal to x tilde divided by 3 factorial x minus x tilde cube, etc. Up to the nth term. Okay, so that's how we could just expand this in this series. Okay, so that gives us a relation between f of x and f of x tilde x minus x tilde. So I could take the difference between this. Okay, so that tells me that the delta f, which is the relation, which is the difference between f of x and f of x tilde, is related to delta x tilde, delta x, which is the difference between x and x tilde, is through the derivative of f to first approximation. Okay, so that's what we would write here. So to first approximation, I could just write f of x minus f of x tilde as f prime of x into x minus x tilde. So what I said here is I am assuming that this delta x, which is x minus x tilde, is pretty small. So as I go to the higher terms in the series, they go to 0, okay, because it decreases pretty fast. It's delta x squared by 2 and delta x cubed by 6, etc. So if delta x is small, very much smaller than 1, much smaller than 1, then it would just reduce very fast. So I can, to first approximation, assume that f of x is simply f of x tilde plus f prime of x into x minus x tilde. That's what I have done here. Okay, so that gives us the propagation of error. So how does the, if I now ask me the question that, sorry, there is an f prime here, it's a mistake. So if I ask, you ask me the question that if I make an error in x, the representation of x, so what is the error in delta f, and that's given by this, delta f, that's f prime, that's the derivative of f at x equal to x tilde into x minus x tilde. So if it's a sharply varying function, if the f tilde is f prime is very large, then that will introduce large errors. So we can actually generalize this idea into functions of more than one variable, and then we would again expand that in a Taylor series. So the Taylor series only up to second term here. So we are only interested in the first approximation. So we are given the series only up to second term. So that is, say, two variables u and v. Okay, so then I would say that f of u v, that is the real values. So the next approximation would be the f of ui vi. Okay, that, well, I here I mean the next approximation to this. Okay, so if I take the I plus 1th digit approximation to ith digit approximation, okay, then I would say that f of ui vi and the derivative of that evaluated at that values of ui and vi. Okay, so f, the derivative of f with respect to u evaluated at ui and vi multiplied by delta u, and the derivative of f with respect to v evaluated again at the ui and vi multiplied by the error in v between the two approximations. Okay, I plus 1 level approximation, digit approximation to ith approximation. So the first term here involves the first order terms are 2, that is one derivative with respect to u and another derivative with respect to v. And the second order terms now have 3 terms. One is a second derivative of the function with respect to u, again evaluated at ui and vi, multiplied by delta u squared, and plus 2 into the second derivative of the cross derivative, that's the cross second derivative, that is del squared f by del u del v multiplied by delta u and delta v, plus second derivative of f with respect to v multiplied by delta v whole square. So again, to the first approximation, the error in f due to error in u and v would be given by the derivatives of these functions at that value multiplied by the error in the delta u and delta v. Again, you know that we don't know what the actual value of these functions are. So if we have, the only thing which we are trying to address here is, if you if we have an idea about how much is the error here, then how much of it is propagated into the function evaluation. That's the only thing which we are trying to understand here. So okay, so that's summarized here. So I can keep writing like this. So basically, the delta f here would be the derivative of f with respect to for any number of terms. I generalize this to many number of terms now. Okay, I have many variables x1, x2, x3, etc. up to n terms, and then I have approximations of that as x1 tilde, x2 tilde up to xn tilde. Okay, having errors, let's say delta x1, delta x2, delta xn, etc. Now, if I generalize this whole idea of delta f with two variable thing into n variables, then I would get an approximation like that. Okay. So, any of these derivatives being large would mean that this function will have a large error in that. Okay. So, that is where we stop. We would try to see some of the implementation of these ideas into evaluating errors and propagation of errors in some real problems, okay, as we go along in this course.